coins are tossed. For each head, a die is rolled. We add up the total of the outcomes in the dice. Compute the masses of the possible results. So it says that a coin is tossed. Here we can use this spreadsheet to have a record, right? To keep a record of the number of heads. Making this spreadsheet, right? To have a record of in this case how many heads we get. So we just dub that as n, right? We can have 0 heads, 1 head, or 2 heads, right? So please tell me, what is the probability that we get exactly 0 heads? So what we have is just 2 spots, right? So we can have a head and a head, and that's 1/2 times 1/2. But we can also have 1 head and 1 tail, or we can also have 1 tail and 1 head, or we can also have 1 tail and 2 tails. The probability of having exactly 0 heads, well, it matches which one? This one, right? So that is 1/2 times 1/2, right? So that's 1/4. Now, please tell me, what is the probability of getting exactly 1 head? We're talking about this event with 2 elementary events, right? So the probability of getting exactly 1 tail is the probability of getting this particular outcome, and this one also, right? So the probability of getting exactly 1 head is 1/2 times 1/2 plus 1/2 times 1/2, right? So that's 0.5. And finally, the probability of getting exactly 2 heads is just this event here, this one here, and that is also 1/2 times 1/2, that is 1/4, okay? So as we can see, well, the sum of all this is just 1, and we are correct. And now I will put here the outcomes that we can get from the sum in the die. So let me see. It says that for each head, die is rolled. Okay, so we can have up to 2 heads. And we need to add up the total of the outcomes in the dice. Okay, so that means that the possible outcomes for the sum of the dice ranges from 1 on 2, 3, 4, and all the way up to what? 12. The maximum value that you can get from the sum of 2 dice is just 6 plus 6, and that is 12. So should you have, for instance, I don't know, 3 dice, right? Instead of having that the maximum possible value is of 12, then the maximum possible value in that case would be 6 plus 6 plus 6. 3 times 6, that's 18. So in that case, we would have these values would range from 0 and all the way up to 18. I am going precisely from 0. Now, do we really need to take into consideration number 0 for this particular experiment? The result says that we should consider 0, right? The answer says that we are fine considering 0. But do you see that? Do you see why we need to take into account number 0? If you have 0 heads, then you do not roll any dice at all, right? So in that case, that you have 0 heads, then you do not roll any dice at all. So in that case, you just get the value of 0 in the sum with probability 1. Here we have the distribution, right? Well, the masses of all the outcomes. So for instance, what is the probability of getting a sum of 1 when you roll 0 dice? Well, the probability of doing that is of 0. What is the probability of obtaining a 2 when you roll 0 dice? The probability of that is of 0 because you have no numbers to add. What is the probability of getting a result of 0 when you roll 0 dice? Well, in that case, the probability is just 1. Things begin to become a little bit more interesting when we have to roll 1 die, right? So in that case, the probability of obtaining a 0 is just of 0. But what is the probability of obtaining a 1 when you roll 1 die? The probability of getting a 1 is of 1/6, and that is just the same for all the others. So what I'm trying to say here is that the sum of all these results should be of 1, and also in this case. So the sum of all these results should be of 1. Now, as long as we have that, then we're fine and we're very happy, and we are going places. Now, say that you get 2 heads, right? So that means that you're supposed to roll 2 dice, okay? So in that case, what is the probability of obtaining a 0 as the sum of the outcomes in the dice? 0. What is the probability of obtaining a 2? The probability of obtaining a 2 is 1/36. Why is that? Well, because we can get a 2 by means of obtaining a 1 in the first die and a 1 in the second die. So in this case, we have just 1/6. Oh, but what am I doing? I already wrote that in the former column. So I just have to do this. So what is the probability of obtaining a 1? Well, we just need to take 1. Now, what is the probability of obtaining a 2? 3, sorry. So a 2 in the first die and a 1 in the second one. But there's another way, right? The way in which you can get a 3, like this 3 here, is by obtaining 1 and 2, or 2 and 1. What you need to do is to obtain a 1 and a 2, or a 2 and a 1. And you see, at the same time, when I say and, I use the times operator. And when I say or, I use the plus operator. So this is just very elementary. It helps us to have a model in mind. It's about a way to translate what we say into what we write. So how do we get a 4? To get a 4, we need to get a 1 and 3. Or we could get a 2 or a 3 and afterwards a 1. So that's how we do it. Now, please observe the fact that well, all I do is going this way. So say that in here we have the mass function repeated itself. So we have the first time and the second time because we have 2 dice. So what do we do in the first one? We go 1 and 3, and then 2 and 2, and then 3 and 1. So what I'm trying to tell you here is that if I have the mass functions of the first die and of the second die here, right? Then I have to do something like this. I go upside down in one of the distributions, and I go upwards in the other one. So now I am showing you how to convolute 2 random variables, right? And I am doing that by means of showing you a dance, right? So here is our step. We need to go upwards with one of our hands, and we need to go downwards with the other one. So I am talking here, I'm talking about a way, an algorithm to convolute random variables. If I need to calculate the probability that we get a 5 with 2 random variables, and that is in the sum of 2 random variables, then we need to go from 1 in the first one and in 4 in the second one, or 2, right, and 3, or 4 and 1. So even when I'm using the same mass function for both dice, right, I am doing this. So this is the dance of the convolution formula. That's what I'm doing here. I'm dancing. Afterwards, we need to take 4 and 1, and also 3 and 2. Yeah, 3 and 2. That's it. Now, in order to get the 6, we need to get 1 and 5, or 2 and 4, or 3 and 3, or I think I made a mistake here. So here's what I'm gonna do. I will just copy this here, right? So we can have a little bit more clarity, okay? So to get 5, okay, we need this and that, or this and that, or this and that. Okay, so this is the one for the 6. So allow me to put it right here. Yes. And to get the 5, that's easier because we need 1 and 4, or 2 and 3, or 3 and 2, or 4 and 1. That's it. Now, to get the 7, we need a 1 and a 6, or 2 and 5, or 3 and 4, or 4 and 3, or 3 and 5 and 2, or 6 and 1. So here you just have the full step with all of the distribution of one die. As you can see, number seven is the mode of the distribution. What does that mean? Well, it means that number 7 is actually the most likely number to get when you roll 2 dice and you add the outcomes that you get in the dice. So so far, number 7 will be the most likely of them. However, it is not the largest of the values that you can get. For instance, you can get also the 8. So how do we get an 8? Well, in order to get an 8, you can get a 2 and afterwards a 6 or a 3 and afterwards a 5 or a 4 and afterwards a 4 or 5 and afterwards a 3 or a 6 and afterwards a 2. So as you can see, this number here is repeated, okay? What I mean is that this number with this one here. What will be the probability that we get a 9? So in here, to get a 9, we'll get exactly what your colleague just said. So for a 9, you can just have a 3 and afterwards a 6, or a 4 and afterwards a 5, or a 5 and afterwards a 4, or a 6 and afterwards a 3. So in order to get a 10, what do? Okay, we can go first 4 and then 6, or first 5 and then 5, or first 6 and then 4. Because in here I should have H9, I think, there. So of course the number was correct, but that was just because I have 1/6 for all of the results in the support. However, I definitely needed to use the correct reference. Now, to get the 11, what do we need to have? Okay, it's just 2 ways: a 5 and a 6, or a 6 and a 5. And of course, to get the 12, there's only one possible combination, which is the 6 and the 6. So now we are very happy because the addition of all these numbers is just of 1. Now, I want you to take a look at this. What if we just plot this? So when we insert a plot with these results, right? Okay, I'm gonna exaggerate it, and I am not going to use a histogram. So I will use just lines. Okay, so I am using just lines. Now, this is an exaggeration. This is an exaggeration because I should be using a histogram rather than just a plot of lines. However, the reason for which I justify this exaggeration is that I want you to acknowledge one thing. Do you know what is the name of the distribution of 2 uniform random variables? The name of the sum of 2 uniform random variables is precisely triangular distribution. Now, can you guess why? So, but this is not precisely the result that we were expecting to get, right? We need something else, because right now all we have done is to, well, first we just put the distribution of rolling 0 dice. Oh, nice. Then we put the distribution of rolling 1 die. Okay, nice going. And in here we put the distribution of rolling 2 dice. But still, we don't mean to find precisely this. What we mean to find is the probability that S equals S. Now, this column here represents the probability that S equals little s given that n equals 0. That is what we have in the first column. In the second column, this one here, what do we have here? What we have is the probability that S equals S given that n equals 1. Actually, we have the 1 as the header of the column. In the other case, we have the 0 as the header of the column. And what we need to get is the probability that S equals S. Now, so you need to get the probability that S equals S. By the way, in here, in the top row, we have the probability that n equals n for little n equal to 0, 1, and 2. So maybe there is some result in the theory of probability that might help us to do this. And right, okay, what is the probability that S equals S? This is the probability that S equals S given that n equals 1 times the probability that n equals 1 plus the probability that S equals S given that n equals 2 times the probability that n equals 2 plus the probability that, okay, S equals S given that n equals 0 times the probability that n equals 0. Do you know if what I'm doing here has a name? This is just the theorem of complete probability. So in here, we just need to use the theorem of complete probability or the theorem of total probability. So by virtue of the theorem of complete probability, all we have to do here is to use the function sum product of this here with this here. And then we need to fix this range here, and that's it. And then all I have to do is to copy this formula and to put it in all these cells. And finally, I can just compute what is the sum of what I just did. Now, I will compute the expectation of the random variable S. Now, we can do that in two ways. The first is just to take the product of the expectation of n times the expectation of x. So it's really simple to do that because the expectation of n is just some product of what with what? Of these probabilities with this range. So that is just the expectation of the coins, right? And we need to multiply that with some product of this from 0 to 6 and this from 0 to 6. So what we get from this multiplication is just the expectation of n times the expectation of x. And we get, in that fashion, 3.5. Okay, that's cool. But there's yet another way to calculate the expectation. What is it? Well, we can just use the definition of the expectation with the support of the random variable s and the mass function of the same random variable. So what if we take some product of this with this? Oh, that's a miracle. We just got the same number. In the first one, for this one, I did the expectation of x times the expectation of n. For this one here, I did, for the expectation of s, I just took the sum from s equal to 0 to 12, right? Of what? Of s times the probability of s. That's it. Now we can do just the same thing with the variance. So we can use the two ways in which we know we can calculate the variance. First, write that we need to take the variance of x. The variance of s is the expectation of x squared times the variance of n plus the expectation of n times the variance of x. So let us do it. So I write now the expectation of x. I need to put the expectation of x and then the variance of x. Okay, the expectation of x equals I don't know what, the variance of x equals I don't know what. Then we need to put the expectation of n, which equals I don't know what, and then the variance of n, which equals I don't know what either. And then in here, I need to put the sum product of the expectation of x equals the sum product of these values here with these other values here. That's the expectation of x. Now the variance of x, to take the variance, what we'll do is to take x minus x squared. So we need to take 1 minus the expectation of x, but this one needs to go fixed and then square, right? So this works for all the values between 1 and 6, and the variance is just some product of these values with these values here, right? So that way we get the variance of x. And to get the variance of n, we just need to get some product of these values with these other values here, and that's it. So the expectation of n equals 1. And well, here I will just compute what? N minus n square, like this. So now we just need to take n, which is this, minus the expectation of n, which is here, square. Oh, I see that I made a mistake here. So I meant n minus the expectation of n, sorry. And the same goes for all these values here. I need to have x minus the expected value of x here. And well, the variance is just some product of these values with these other values here. So there. So I just used the definition of the expectation and of the variance for both random variables, right? And in order to get the variance of s, well, we just need to substitute these values into the formula that I wrote with my unicorn marker. So the expectation of x equals this number, square, times the variance of n, which is this, plus the expectation of n, which is this, times the variance of x, which is this. I got a 9.04. And well, I can also compute the variance of s by means of just the definition of the variance of s, right? In here, for all I just did, with this formula, I used what we learned in the previous chapter. All we need to do now is to take that the variance is just the expectation of s minus the expectation of s squared. So we need just to get the s minus the s minus the expectation of s, which is just s minus, that should be a little less, s minus the expectation of s square. Okay, this is an I like this. Okay, and then I get this minus the expectation of s, and then square, right? And this one starts at 0. Why? Because the support of the random variable s, that one starts at 0. And now we just take some product of these numbers here with these other numbers here. Oh, that's a miracle. We got the same number. We just got that the formulas that we learned in the previous chapter are actually correct. Now you're eager to test your new skills in some other example.